Hello, community. So great that you are back. We have brand new research by Harvard and MIT. And the first sentence of the new study is, the promise of our foundation models, of our AI models, of our large language models, it relies on a central presumption, that learning here to predict the sequences, the next token prediction, can uncover deeper truths, or in the best way, even a world model. And you might say, yes, of course. No, because we also have this idea that a smaller language model learns basic patterns, a large language model learns more complex relationship, and the truly massive model by OpenAI, GPT-5.03, they will suddenly wake up and we will have here the emergence here of intelligence. A theoretical physicist would call it here a world model, so a transformation here from statistical patterns to a world model. But yeah, here we have it, AGI, ESI, and today I can give you an answer. Let's explore. Now, interestingly, Harvard and MIT, they started here in theoretical physics. Now, what a coincidence, say, hey, Kepler painstakingly observed here the planets, and he devised laws that predict the future position of the planets in the sky. It was a triumph of predictive power, no? But he didn't explain why the planets move this way. Only Newton provided here the why, the inherent laws of nature. Because Newton discovered the underlying world model, if you want. Yes, I'm switching here between AI and theoretical physics. The world model is the laws of the universal gravitation and motion of the planet, and this is it. But you know what was beautiful? Newton's model wasn't just to predict something, the next token. It was an explanatory model that was able to generalize to other objects like apples or cannonballs or whatever. So here we have it, the Kepler and the Newton idea. So where are we with AI? Our foundation model, are the Keplers of our time. And they are incredibly good at the prediction, What the next word? What is the next token? My goodness, it can write beautiful essays, so general. But the question is, are our language model implicitly learning now already a world model? So a deeper Newton-like understanding of the concept of the rules of the causal structure that govern here the motion of the planet, the data that we see in AI? Where are we? Are our current language models, are our foundation models, a Kepler or a Newton? It couldn't be easier, ne? Well, as I say, if our language model, MIT argues, are just brittle pattern matches, just Keplers, we can't trust them for some high-stake application like scientific discovery, medicine, finance, or autonomous driving. However, if foundation models are truly learning here the deeper world models, they could revolutionize science forever. So, the question is simple. Does AI work, or does AI understand what it is predicting? And here we have a beautiful experiment by Harvard and MIT, and they tell us, for the orbit of Neptune, this in a numerical simulation is the true force that the sun is here, the gravitational force that is here imprinted here on Neptune. You see this here in this arrow, the vectors. And now here you see the prediction by a transformer model. And this is an amazing prediction. So they had to design a clever experiment. And the beauty in their new study is the inductive bias. An inductive bias is a model set of assumptions about the world which it uses here to generalize from limited training data. An LLM that has truly learned here the Newtonian physics, the real law of nature, will have an inductive bias toward those functions that obey here gravitational inverse square law. Inductive bias towards the real laws of nature. And the central thesis of the new research paper by Harvard and MIT is, a foundation model has learned a real-world model if, and only if, its inductive bias aligns with the rules of that world model. Simple, elegant, but extreme powerful. So here we have it. We have now an inductive bias probe that we have. As an input, we have a world model and a foundational model, a transformer model, learns function from the data. And now step one is, We fit the foundation model to syntactic data sets. I'll show you this in a minute. And we extract here the learned function. I'll show you this in 2 minutes. And then step 2 is we just compared the learned function to the given world model. And then we see if it's true. It couldn't be more elegant, yeah? Now, you have different approaches, but whatever you try to understand here in the internal mechanism of a language model, this is challenging. And therefore, MIT and Harvard said, you know what? We have a different approach, a much more simpler approach. We just look at the result. So, the idea here of this inductive bias here offers here a beautiful connection between the foundation model or a large language model and their inherent world models. Because physicists may train here a foundation model on a sequence of planetary orbits position. No? And since planetary orbits here obey the Newton mechanics, they might hope, and we all hope, also as an AI scientist, we hope, that the model, the language model, has an inductive bias toward those mathematical functions that really describe here the laws of nature, at least here in the classical limit here, the Newtonian mechanics. So we predict here the force vector between two planets, so here the sun and the planet. The authors from Harvard and MIT developed now an inductive bias probe for testing whether the foundation model's inductive bias really matches here the postulated world model's state structure. So the inductive bias probe repeatedly applies here a foundation model to a syntactic data set. I'll show you this in 3 seconds. Consistent with the world model and studies the extrapolated functions together. Here's the result of Mercury. Mercury, a little bit more of an elliptic orbital shape, and the predicted force. And you see where we are heading. Now, a world model, again, the definition. You start with a domain where the underlying rules are known. This is our postulated world model. Now, in physics, it's easy. We are defined by the masses, the position in the orbit, the velocity here of the planets here in the orbit, and the rules are simply, and the classical limit, the Newtonian laws. We don't have to go with anything close to field theory or whatever. And we repeatedly create tiny new training data sets now for the fine-tuning of the LLM. Ne? And each data set, of course, is consistent here with the world model, with the real laws of nature. And you fine-tune now, we fine-tune now here a pre-trained foundation model on each of these small syntactic data sets. And you then observe the function that this fine-tuned model has learned by seeing how it predicts on the training data set, the held-out data set. Of course, it's the classical way. But the key question is now, do the function that the large language model chooses to learn internally respect the structure of the true world model? Is it really here the law of nature? So they introduced 2 primary metrics here for the task with classical discrete states now, and they have an inductive bias towards the respecting state. It's very easy. Just imagine you have 2 different input sequences that lead to the same true state, so given the same output. Now, a high score of this particular metric means that the model doesn't create artificial distinction. It is really saying, okay, same true state, same output, great. And we have an inductive bias towards distinguishing the states. So if you have 2 input sequences that lead to different true states, so different outputs, a high score here means that the model successfully tells, hey, those are different states. Couldn't be easier, ne? And a language model that has learned now, this fine-tuned model here, an inherent world model, the laws of physics, should score high on both metrics, on both benchmarks. Now here we have it, July 9th, 2025. For me it is today, from Harvard University and MIT, and they did it. They did this big experiment. They wanted to find out, do we have ASI, AGI? Is really the emergence of intelligence happening? And we don't want to have a mechanical understanding. Is there intelligence created within an AI? But we just do here a simple probing. Such an elegant solution. So what was the setup? A transformer trained to predict the next position of planet. This is Kepler in many different solar systems with many different masses here. You can go from Mercury out to, oh, Pluto is not a planet anymore. I still think Pluto is a planet. So yeah, so it becomes extreme accurate at this. No, this is a perfect Kepler system. And this model is then fine-tuned on a new task. Remember, here we just have the orbital information. So here Kepler just sees, okay, I have here on 364 days of the year, I know exactly where the planet is. And then on the 365th day, so the next token, the next time step, I can predict here the orbit, the X, Y, Z coordinates. This is Kepler. But now we say, we fine-tune now you on a new task. Given that we have the position on your elliptical trajectory, you should now predict, as a fine-tuned LLM, the gravitational force. So do you understand? This is the core element now of the real-world model. This is the core of Newtonian world models. You just predict the gravitational force that acts on this planet. In the simplest classical limit with masses and distance. And here you have it. They did the big experiment. This is the Earth. And this is the Earth predicted here by the transformer model. After the pre-training, after the fine-tuning on real data. And they even did this not only for Earth, for all the other planets. Mercury, Venus, Mars, Jupiter, Saturn, Uranus, Neptune. Beautiful. And you see it's perfect chaos everywhere. The fine-tuned transform architecture, when it had to predict the force, being perfect in being a Kepler to predict the next token prediction, to predict the next location of a planet in its orbit, to 99 point I don't know what accuracy, it failed completely to predict the force. So, but which model did it learn? The true Newtonian classical limit here? No. They did something clever, Harvard and MIT, and they could understand what formula, what function the LLM internally used for this prediction here of the gravitational force towards the sun. This is it, for example. So the result is the model completely fails. Absolutely. It is not just inaccurate. The form of its error, it's what's revealing. Yeah? And the authors used here beautifully symbolic regression as a methodology to discover the inherent laws, the physical laws that the LLM actually learned, not the real correct laws of nature. But the LLM built something here within its neural network. And it was some absolute nonsensical physical formula. And they could look into this, and with symbolic regression, they could extract a mathematical formula. So what physical law the model actually learned? And it was this. So it was a complete failure. And you know what? It is even worse. It is even worse because the language model recovers here a different nonsensical law for every different solar system with different masses of the sun or of the planet. Whatever you put in, it's always creating a new law. It's never understanding that all the planets are governed by one law. The AI is not able to solve this. Absolute failure. So the model did not learn a universal, a generalizable world model. It learned here a variety, a collection of complex, brittle, non-physical heuristics that were just good enough to solve the original trajectory prediction task, but nothing else. No further intelligence, no further understanding, no further coherent world model. And you might ask, what is the deeper insight? We are here to learn on your YouTube channel. Of course, I ask myself, hey, if it's not learning the world model, what the heck is this LLM learning? And why and how? And give me all the answers. And this is now where the paper delivers its final crucial insights here for AI scientists. The failure of the model is not a random failure, it's a systematic failure. And we can examine this. So let's do this. So if you are a little bit in theoretical physics or mathematics, you say, hey, can you give me a different view on this? Can you give me a different perspective that I can understand it? So this here is now my understanding. This is not Harvard, this is not MIT, this is my little brain. And I say, imagine, I give you the point here on a graph, no? Not in the orbit. I just say, hey, I have a two-dimensional coordinate system, and I give you 3 points here. No? And then for x equal 1, x equal 2, x equal 3, and then I ask you predict the value for x equal 4. So you see, now so we understand where we could go. Now, a Newtonian model would say, hey, I learned the underlying function. This is here square. So it would predict for x equal 4 the correct y value given this particular function that defines y given the parameter x. But what we have is a Keplerian model. No? You could learn, the AI could learn an extremely complex wiggly function. Not at all a square function, but a high degree polynomial approximation or a combination of sine waves, some crazy Fourier transformation that is absolutely nonsensical that just so happens to pass exactly through the 3 points given, 1, 2, 3. So this function might also give a prediction that is very close now to the real 16 for x equal 4, making the model look very smart in the Kepler prediction of the next position in the orbit of the planet. But it fails to come up with the real law of nature. This is here this simple law. It constructs here some crazy polynomial mathematical function, and it fits those 3 elements, and maybe it can even predict here the 4th element. But this is something that is not sustainable. So, what a transformer did, it learned a highly complex mathematical function that is an exquisite approximation of, let's say, again in my example, the orbital path it was trained on. It is just an overfitting LLM. That's it. It doesn't generate deeper insight. So when you fine-tune a model and ask you to do a new task, but of course a domain-related task, out of distribution task, predict the force towards the sun, predict the gravitation. So this is what's really why the planet is in orbit around the sun. You are essentially asking that wiggly function that the LLM has internally created to do something it was never designed for. The function it learned looks nothing like a true law of physics. So its prediction of force are absolutely nonsensical, a pure nonsense, pure hallucination. But it is not just a hallucination, it is a guided structured process. But horribly wrong. Look at Venus. Look at this. At the orbit, now if you go for one position, you have here this position, okay, almost a little vector on the other side of the sun. Then we have in the next step a massive vector wanting to leave the solar system. The very next step, another massive vector, maybe tangential here to the sun, then another vector just going retrograde. So to predict the force here, the next token prediction of an LLM massively fails here. Even it was trained to give the next position in the orbit, but the force vector, the fine-tuning here, has no inherent understanding of the model it can build upon. When we calculate now the force of this on the planet on this position, you see the inherent understanding of the LLM tells, yeah, it's a complex sinus. No, absolute nonsense. Whatever goes on in the continuous augmentation and a chain of thought, if it starts with nonsense, guess what is the second and the third step? So those extracted laws are the evidence here, and they did a damn good job because they used symbolic regression to find those formulas. And they tell now a model's ability to achieve a high performance on a specific predictive task, like predicting here the next orbital position of Venus, is not a sufficient evidence, and also not to predict the next token in the correct way, is not evidence that it has learned the underlying generative principle of the domain, that it has developed intelligence, hyperintelligence, superintelligence, general intelligence, intelligence that you like. Why? Because the model has simply found an internal shortcut. So the next token prediction objective did not pressure it enough to find the real solution, an elegant, simple Newtonian law mathematical formula. It just pressured the system to find any function that works for this particular configuration, no matter how complex or unlogical or unphysical or just pure nonsense. For the moment, it was good enough for the AI to predict the next position in the sequence, and all the human users said, oh, wow, unbelievable what AI can do. And the authors tell us, hey, this discovery is a profound cautionary tale for the field, urging us to develop better methods to understand what our models are really learning when we think that AI is intelligence. And you might say, hey, but wait a minute, buddy, hey. Maybe the task is simply impossible to solve for this kind of an LLM. The complexity level is too high. The model is not deep enough. There's not enough layered. The size of the model is not good enough. Maybe the architecture is not there. Maybe we should use a Mamba too. Maybe we should use LSTM combination. Maybe we should use multi-agent configuration. And Harvard and MIT tell us, yes, we thought about this. We understood we needed a control group. So we created something here. We call it an oracle. It's an AI equivalent of a control group that we have in medicine. And oracle is not meant to be a realistic model. It is just the perfect idealized benchmark, if you want the upper boundary. An oracle is simply a model that is given here a cheat sheet. So while the foundation model, the transformer model that we have, only gets to see the raw sequence of the data, so the planet's position over time, so the sequential data, this oracle is given here the truly underlying state of the world model, the real explanation, the real Newtonian laws. We just want to have here the upper bench. So we give everything, planet mass, sun mass, planet position vector, velocity vector, and then we train the oracle. It's just the perfect model if you want, the ultimate benchmark. It's like if you're a student, the oracle is like a student who is given the complete textbook formulas for gravity and motion during the exam. So this means this student or this oracle system has direct access to the ground truth, to all the rules that govern the dynamic of the system. So there's no open question. You just have to learn it. So if we establish oracle as the best case scenario, the upper bound, then we can say, hey, if we fine-tune now this on the predictive force, is it possible to solve the system? And the oracle model shows us, yes, I can solve it rather easily. A model can predict the force vectors in the correct way if it's operating on the correct underlying information. So this means that the foundation model failure isn't because the task is not possible for the model. It fails because the foundation model did not successfully extract the correct underlying information from the sequence data. But in general, you can solve this with this model. And they calculated all of the same for the oracle model. And you see it's perfect harmony. Perfect, great, beautiful, everything works out fine. They even have here, with the regression here, the correct mathematical formula. And I to myself, I said, hey, but wait, what you just told me? We have given everything to the oracle model, the correct law of physics, so of course it knows the answer. And then I thought about it, I said, hey, I made a mistake in my thought. The oracle is not trying to discover Newton's law. We have given it a Newton's law. The purpose of the oracle in this particular configuration in AI is to answer a different, but a very specific question that goes, hey, if a language model had successfully discovered and internally represented Newton's law from the training data, would it be able to perform well on our force prediction test? This is the reason why I need oracle. So I almost made a mistake, Think of it like this. The entire premise is we are testing whether the foundation model, our LLM, is or has internally built a Newtonian world model. But we can't see inside here the neural network itself. So we need a way to test this hypothesis indirectly. And this is here why the oracle is here our perfect reference model. So we are not testing the oracle's ability to learn. It is a reference what correctly learning looks like on this specific task. So the conclusion is, since the behavior of the foundation model does not match the behavior of our reference model here, the oracle, the best models, the initial hypothesis must be false, that it learned it. So the foundation model has not learned the true physical state, the real laws of nature. This is here why we need here the oracle, the control group. They did this thing also with other galaxies on different things, on a chess game, on whatever. I just showed you here the physical part. And they estimated here, when they did here, like for galaxy approximation, the dynamic of a galaxy, they had a ground truth law of the classical limit here of gravitation. And they said, look, this is what we found for different galaxies that we provided here, just the orbital data to this AI system. Now. And then with symbolic regression, we could recover here the incorrect force equation that is the inherent model of the AI of our large language model. Now. But it's never recovering here the real world model now. And you still might be skeptical, like I was, and I said, hey, but wait. What was the exact transformer model? This study was done by Harvard and MIT. Now, unfortunately, those at Harvard and MIT are kind of clever, and they said, you know what? To eliminate every non-controllable influence, to have an absolute controllable environment of our AI system, we built a decoder-only transformer architecture with 100 million parameters, tiny, with 12 layers, 12 attention heads, 7, 6, 8 dimension, embedding dimension. We pre-train it exclusively on a massive synthetically generated dataset of planetary orbital trajectories. Nothing else. No English, no poem, no nothing. This is here a highly dedicated expert model with 100 million parameters, free trainable parameters, but it's just one reason, planetary orbital trajectory. The task is the next token prediction, where a token was a coordinate of the planet position. Building this from scratch, clean, specific data, created a perfect controlled environment. Beautiful. So this setup isolates now the learning process itself in a way that we can now ask, can a sequence prediction of the orbital position alone uncover here the underlying physical laws? And I think the answer of the paper is absolutely a resounding no way. Sequence predictions are not enough to uncover physical laws. There's no emergent intelligence in these AI models. And the authors went another step further, and this is amazing. And they said, you know, maybe it's just a transformer architecture problem here. Multi-head self-attention, cross-attention. What if we take other AI architecture models? Maybe this is transformer specific. Maybe this is not a general AI feature. And they said, what about RNNs? What about LSTMs? What about Mamba or Mamba 2 architecture? This new class of structured state space models. And you know what? They all exhibited the same fundamental failure. This is the state of AI, July 2025. And still, there was a voice in my head that said, but wait a minute, no? What about the big guns that we have? What about the commercial? Forget about open source and everything. What about commercial large language model? OpenAI O3, Claude 4 Sonnet, Gemini 2.5 Pro, the best of the best. Now, of course, they could not fine-tune this model because they are highly proprietary models and you would spend, I don't know, a fortune to just be able to fine-tune those models. So what they used was the next best thing, in-context learning, ICL. Beautifully, works great. Said, okay, we had to modify our methodology a little bit, but the result was they failed too. Unbelievable. Absolutely unbelievable. And instead of applying here deep physical knowledge from their training, they have been trained on all of Wikipedia, all of mathematics textbooks, all of theoretical physics textbooks, all of astrophysics textbooks. They have the knowledge in their training data. They defaulted to extreme, simple, incorrect heuristics. I don't understand how is this possible, but okay. So these models often concluded that the force depend only on one of the masses on a two-body problem and completely ignoring, for example, the inverse square law of the distance. But I mean, come on. OpenAI O3 knows everything of Wikipedia, and it fails to apply it. So this means to know something is not equivalent in AI with to apply it. And even those powerful models don't spontaneously access or apply a coherent world model when faced here with null scientific reasoning tasks. And this is the formula they came up with. Now, in the regression, they could extract here the internal reasoning, what those models thought that the real laws of physics look like. For an O3, it's just proportional to the mass here of the first body. For Claude Sonnet 4, it is inverse proportional to the mass of the second body. And Gemini 2.5 Pro is here proportional to M1. Absolutely fascinating. They did even more. For the O3, they looked at force magnitudes now for different solar system configurations. Blue is always the LLM model. So blue is here the O3 model. Now, you have here the true force, and this is here O3 says just plain line. Now. Okay, here, solar system 2, yeah, it's a linear force. Solar system 3, O3 in blue, just a line. Solar system 4, just a linear. Unbelievable, they fail amazingly. Just here, solar system 5, you see, okay, it's a linear line, but we have some peaks here, pikes here. Okay, Sonnet 4. Okay, a line. Okay, more or less, yeah, a little bit, and then a line. Then here, just step functions. And here, maybe an approximation. And Gemini 2.5 Pro, this is the first model I see this. Look here, it's almost like the blue is kind of following here. Now, unbelievable. We could have maybe an approximation. We could imagine that it would be an approximation. Yeah? Here, not a step function, not just a straight line, but yeah, this could almost look like a potential. Yeah, this is going in the right direction. And solar system 5, oh wow, this is like an extreme Fourier catastrophe happening. So I think it's amazing. This is an absolute beautiful paper. You have to read this. Harvard MIT published today, July 9, 2025. What has a foundation model found? Using inductive bias to probe for world models inside of our foundation models, of our transformer model, of our LSTM, of our RNN, the different Mamba models. What a beautiful big experiment to tell us AI models just fake it. They have no real understanding. And don't you dare to talk about intelligence in AI. If you subscribe, I see you in my next video.